Now a little more about the grouping. I think I have explained to you already a little bit, but let's do it formally. Like we start, like if we try to think of an algorithmic steps, okay, so we kind of know which boxes are neighbor with each other to start with, right? And then that means each box is a group of one, right? Each box with one is a group of one. And then from the definition, as we know that which box is neighbor of what, we can start grouping, like group 0 and 2, their neighbor. 4 and 6, their neighbor. Why I haven't done 0, 4 and 2, 6? You could have done that in the steps. It's just on which order we are doing. That's all. That's all it matters. Now from this point, so since 0 to a neighbor, we make them group. Now we see what could be my neighborhood groups. Okay, so it seems like your 0, since 0 and 4 also neighbor, and 2 and 6 also neighbor. So basically they have each of these element in this two separate group of 0, 2 and 4, 6, we have a corresponding neighbor in another group. So we make this guy as a bigger group of 4. So that's how mentally, even if we don't think, mentally we kind of operate that we start with a small group, at least we should focus with a small group. Then we need to see how we can make it included into bigger and bigger and bigger group, unless we kind of ran out of ones or we don't no longer like can match the criteria of having the group member of 2 to the power 2 numbers and so on and so forth. Similarly, for this bigger group of 8, we can group these two, 0, 1, then 4, 5, 12, 13, 8, 9. Then we see group of 0, 1 and 4, 5 are neighbor with each other because they have neighbors between them, make a big group. Then rest of the groups, 12, 13, 8, 9, they have also this similar relation between them, make a group. Then we consider these two bigger group, and they have adjacent neighbors with each other, like 4 neighbors with 12, 5 neighbors with 13, 9 neighbors with 1, 8 neighbors with 0. So we make a bigger group. But we do not do this. We cannot make a group of 6 because it will then we'll have a group of 6 element, which is not a power of 2. So we cannot do that. Okay. So now the question become, why this bigger group goes for smaller element. Bigger group goes for the smaller element. Let's try to understand that. For that, let me get back to my previous example, this one. Okay, let's just mark it under example 1, where we are trying to describe our neighborhood. Example 1. Okay. And okay, then this is example 2. All right. So for this, we made a neighbor of 5 and 1, right? Let's say don't worry about this example. It's completely different example on the text notepad here. So 5 and 1 are neighbor, and also made a 3 and 7. 3 and 7 are neighbor. Then we are claiming, according to the maximization of the group, we can claim that. So we can group in this case M1, M3, M5, M7. They are neighbor with each other. So we are making a bigger group, and this bigger group will give me optimized value of W bar and Z. W bar Z. Now, how this is in place? How this works, right? So we are grouping means we are grouping these two, M1 and 5. And also we are grouping M37, which is like this one, right? So this is my original expression. So let's try to put the identity in the same way. we group like this, that too, and then the next one will apply this, and which will essentially will become w bar y bar z dot 1, w bar y z dot 1, which is w bar y bar z, or w bar y z. This equals, now we can write it down like this, w bar z y bar y, which is w bar z dot 1, which is w bar z. So see, it's the same thing. The way we are writing the group corresponding Boolean expression for that group, we can do the same thing just by also doing this identity based formula reduction, right? So here's the power of this visual technique. Instead of doing all these steps manually, we just visually looking into this group of M1357 and inspecting within that group which variables are unchanged. We see that W is unchanged at 0, so we write W bar, and Z is unchanged at 1, so we write Z, and that's it. That's the expression for the group without thinking anything else. So this is what I kind of meant by it's formalizing the algorithmic steps for reduction. All right. So you can well imagine, like with after this discussion, like you are all good software programmer. So think this table, this K-map as a graph, relation and neighborhood graph. And from this, you are starting from one point and you are trying to make a bigger groups of the node. And once you identify these bigger neighborhood groups, from that group, what all you need to do is make the corresponding Boolean expression for that group. It's not a trivial implementation, but it's doable, right? So that's the stepping stone. So now if we can do it in a program in an algorithmic way for 4 variables, we can do it for 5 variables, 6 variables, 7 variables, 8 variables in an algorithmic way. But remember, K-map visual technique is actually applicable for like till 4 variable. If 5 variable, your neighborhood tables would have to be on the 3rd dimension, which is very like hard for as a human to think the neighborhood in a cuboid space. Okay, so after 4th variable, it's basically undoable by human, by visual technique. Okay, but nonetheless, the importance of the K-map, again, as I want to reiterate, is that start the stepping stone for the algorithmic thinking of how we can make a program which can minimize Boolean expression from an SOP like function definition. Okay, so that's the beauty of the K-map reduction process.